Hello. So I'm tasked with building the programming environment that we present to our users on our HPC systems, which we have a variety of. And much like the last person, my background's not actually computer science, but I just wound up here. So Spack just does it, right? Not quite. Not yet. I'm still waiting for the Spack do my job command. But so our build process looks pretty messy. There are a lot of restrictions on our environment that lead to this disaster. And then I'll talk about if it's actually better than it was before and what kind of issues we've had that make it more complicated than just making it turnkey, and how we would like to see it in the future. So for the point that we're at right now in our environments, we find that we've also come across this with the last few discussions of, do you want one or many Spack environments? And it's important to remember that we're also not on the cutting edge of Spack. So as these issues get pushed to new versions, we will eventually upgrade, and maybe they will fix some of our issues, or we find workarounds at the time. There's a lot of fights with the concretizer. Much like others have mentioned, it will do strange things, and it's hard to tell it to stop doing those things. Reuse sometimes works, sometimes it doesn't. And concretization time's not nearly as bad as Fugaku, but that is also a reason against having one monolithic environment. And the environments do grow, but they have common dependencies. So my solution has been to use a lot of containers to make this work, which does utilize a lot of disk space, but I keep being told that memory is cheap and processing is the expensive part, so gigabytes and gigabytes it is. Which has also been helpful in finding the full list of dependencies. There, try as it might, Spack doesn't necessarily know all the dependencies of a package, so we found there were even some that didn't explicitly rely on Python and were still failing if it couldn't find a Python in its own path. So this has been very helpful in finding some of those and making sure we explicitly are installing, because I start from a very minimal container. So I have to explicitly install all those dependencies into the container to get this to work. This does enable us to rebuild certain segments of the stack instead of having to reconcretize the whole thing and rebuild the whole thing. And because reconcretizing is needed a lot of times, but doing the whole thing is just not reasonable. This does also enable some parts to be built in parallel. So we do break out by compiler. Each of those compilers could be run at the same time on different nodes if we manage to break this out into CI like we hope to. And you can even break these out and build them on different machines. So we have our ATS machines that are LCAP-like, so they're AMD CPUs and GPUs. We can use that machine to build the environment for others that don't have that same hardware. But because we have the container that represents that kind of system, we're able to build it on whichever system we like, which helps with having that CI be able to find resources even if one of those machines is down. And we also have a lot of after-the-fact modifications. So we have, when I got there, there was a script. I started like 3 years ago at Livermore. There was a script that was like 6,000-ish lines. It probably grew to 7,000 while we were working on the next iteration. And there's just a lot of ways that our users expect things, ways we think our users expect things, ways we like to baby our users so they don't trip over themselves. Backwards compatibility, old compilers are required. So there's a lot of historical guidelines on our environment that we have to work with, which complicates things. We can't just take what Spack gave us and give it to the users. But because we have these containerized and scripted, at least the fixes are documented. So as we work with Spack to try and overcome some of these, we can have proposals and take them out once they are addressed. I think I've gone over most of this. Yeah, one big issue is Concretizer trying to use a binary cache. We found an issue with that recently, that it will just pull things from the binary cache even if it violates requirements in your packages.yaml. Don't know exactly how that happens, but that has required us to always build from scratch for one of our compilers because it was doing that. And I've watched Greg dig into the Concretizer for me. That looks like a nightmare, so I don't blame them for not fixing it immediately. They've got 1.0 to worry about. But dividing it up by compiler has helped reduce this, I guess, possibility space that it can pull from, so that it tends to make much more sane environments. So here's a bit of an outline of what our workflow looks like. We're running TOS4 on all of our systems, so I have a base TOS4 container. I add those minimal dependencies so we explicitly know what we're using. We then have a container that we have Spack in that builds all the core packages, so like Git, CMake, Python, all the compilers, all the things that can be built by that one central compiler. And then we push that to the binary cache. And we have our per compiler containers, so there's multiple GCCs, multiple Intels, but just for the sake of compression, there's only one here. And each of those builds that stack of software and pushes it to the binary cache. So we also need a coherent environment, coherent module sets. So we have a final container that takes all of those log files, puts them into one environment, and builds from the binary cache. So it's actually relatively quick compared to building out the entire stack in one go. And then we have this monolithic script that tells Spack how to do the modules, fixes all the modules that we found have issues, builds the view, fixes all the views that we found have issues, and then we have a lot of double checking to make sure paths, either in our path or in scripts, actually exist. And we also go through now and make sure everything is our path and not run path, because that also bit us recently. And then we have our final deployment, which we just squash FS up, push out to the machines, and unpack into place on NFS, and that's what our users are able to see. So we end up with about 800 packages at the moment, 26 gigabytes when it's compressed, about 182 gigabytes when it's not compressed. So it's unwieldy. I really leverage RZ Atoms and its 500 gigabytes of on-node memory to have the base container and the final container both in memory at the same time. So what exactly is that long script at the end doing? I went over some of this, but it creates the view and the module sets. But there's a lot of things that Spack doesn't do for us, because Spack does that part, not this. We have a lot of packages that are already built in other parts of the system, not with Spack. So we have to generate symlinks to those inside of our install tree and modules for those in the right place. We also provide a bunch of software in the user's initial path upon login, so they're not necessarily using the system GCC. We can get them by default on something more modern, and then they can module load to get something other than that. And like I said, we scan all the ELF objects for our paths, scripts for non-existent paths, set permissions appropriately. And if we do it well, we can fix all the things that are wrong, and then, or if we do things well, eventually we'll be able to fix most of these things in the Spack install eventually and need less and less of this script, or that's the dream. And we do this because this is what our users require of us, and we have some level of contract with them to deliver exactly what they need. They give us the money, I guess that's fair. Compilers remain on the system for the life of that OS on the system. So we just got new computers in 2024, and we're installing Intel 19 on them because there's still users that need them. When we update from TOS 4 to TOS 5 or 6, that gives us a chance to pare back some of the oldest stuff, but it'll still probably have a 5 or 6 year lag time of that old software still needs to be there. We baby our users, I guess is the way I like to put it. If they have a script, we have to do backflips to keep those scripts from breaking. So we can change a package, but we have to have presented it in such a way that the change isn't impacting or breaking anything they have. An instance of this is a lot of the Spack installs, because it symlinks back to the core installation that has the full hash and everything like that. Their applications will either pick up those script paths or our path to those, and then if we try and replace it with a new updated version, but use the view to kind of obfuscate that, they'll still get picked up in their codes and it'll break things. So we do a lot to make sure we don't break that. Users also do things in weird ways. Andy had the hope of eliminating modules, and apparently a lot of our users like to circumvent the modules. They'll module load to get something, and they go, oh, that's the path that I need. Okay, I'll never load that module again. Here's the path I need. That can never change now. So we have to keep these things going, and there are probably other things we don't know that they do that are heinous, and we have to accommodate. So we try to be as accommodating as possible. Already talked about old compilers, and keeping things working at the time while we develop the new thing has always been a challenge. Some of the other speakers have already talked about this. The old way of deploying the software is you've got a bunch of individuals, perhaps even on different teams, that are each responsible for some subset of the software. They'll each have their own set of scripts for installing that software. If you have to try and move one of those products to a different person, it's just about as hard as learning how to install the package from beginning anyway. You have to pull their scripts, figure out what magical incantation it takes, and you really hope no one leaves, because if all their scripts are just left sitting there with no historical knowledge, that's gonna hurt. So Spack does help with this. We moved on to a better version, which was using Spack, but again, it has some fragility built into it. We had to be a specific user on a specific machine, on a specific node of that machine, using scripts at a specific path within their gigantic tree of scripts. Deployment is another set of scripts that you have to know where they are by what user, and they're going to get synced around by magic that happens in those scripts. So if you go, oh, this is broken, where's the script to fix this? It's almost never going to be anywhere you're thinking is appropriate for that script. So Spack helped build up a lot of it, but getting it into place was a very fragile process. That is why we haven't had a new deployment in quite a while, because I've been updating this. So we want Spack to do most of this for us, but there's some things that it doesn't quite match. We want it to be reasonable, and as someone already mentioned, mixing the compilers is just not going to work. So we've had to clamp down on it using the separate builds. Minimal duplication of packages has been a trial, like keeping every compiler from building its own zlib has been obnoxious. And there's lots of others. But then when you break out the compilers into different sets, there's a lot you do want them to use from a different compiler for the low-level stuff. So try and balancing those two requirements takes some effort. Not replicating things that are already on the system takes work. I think the automatic external detection helps with that quite a bit, but there's still some art in there for determining what the variants of that thing are. And Spack, I guess, just has some promises that it doesn't quite deliver on. So the root install directory will be exposed in the module sometimes. That doesn't get replaced with the view. So we just have to go back and clean up after those. We want it to be reproducible, with the concretizer doesn't want ever. Reconcretizing will just switch hashes because there's a lot of undefined default variants or default values, or even things that you can't specify on the command line will get switched and cause the hash to change. And you just don't understand why it's not the same as the last time. You didn't touch that spec at all. So trying to keep Spack from doing that takes extra effort. Obviously, the requirements being violated by the binary cache is painful. And then upgrading Spack breaks a bunch of recipes, which hopefully breaking them out into their own repository will help fix. And then functional. We think the directory structure should be more understandable than encountering hashes that mean nothing to me. We can do that with our views, but we've had to do a lot of work to make sure that looks sane. And then the modules also will end up having short hashes that you then have to go 2 more directories deep to find. And some of that we may be kneecapping ourselves, and in some of that Spack just makes it that way. Pointing to things that actually exist, we do that ourselves. Libraries not finding symbols. Spack enforces quite a bit of this by trying to RPath everything, but there's some things that are just installed by not Spack, either pip or unpacked from a tarball or what have you. And so we have to go back and find those. And it'd be nice if Spack could do that. But then again, Spack doesn't always know the final place that it's going to be put into, so some of those have to change. And then obviously there will always be some amount of packages that are not built by Spack, but we still want to present to the users as part of the environment. So I don't know what the best solution is for that. Maybe we could external and add it to the root specs. So we've had a lot of debugging. I've bothered Greg about 5,000 times. But for the first steps, before you start going to them, output with -d is almost going to always be part of what they ask for. So start there, take a look at it yourself. You might find something that's, oh, yeah, no, I can fix that, and just go fix it yourself. Checking the provided logs. They're like config output's a very helpful log. It's very long, but when you can find the right place, it'll show you exactly what it was running and exactly how it failed, and probably give you enough information to start looking at things yourself, or at least present better information to the Spack developers when you're doing that. Even for successful builds, you can find a lot of this information under the .spack directory where it is, or you can tell it to keep the stage. I've had another user come to me quite a bit asking about issues, and because they're also on a slightly older version of Spack, a good first step is just go to develop, see what that package looks like now, and there might already be a fix for your issue. Just because the packages aren't broken out, they can't pull those in. So that is also a great first step for finding any of these. Existing issues can be difficult. I think they listed up a much smaller number of issues that are active, but When you look at the GitHub page, it says like 2,500, which is a bear to try and search through. The concretizer remains a black box, so I go to Greg or Peter or someone to try and demystify that for me. But if it's in there, it's probably going to be a difficult hack to fix. But there's also the Spack Slack weekly calls, and I'm lucky to have the devs right down the hall when they're not on travel. So the ideal that we're kind of shooting for right now, at least a realistic ideal, we would like to automate these builds. Getting them into Jacomar runners on our GitLab CI would really help to take care of the build process, so calling everything just the right way, we can kind of document all of that. Building branches before merging would be great, because that way we can build and test, say in a container, without having to impact the production instance. And we can debug those builds that are automatically done much faster. Parallel builds, obviously, no rebuilds for untouched stacks. I think that kind of gets into like the CI, the GitLab CI side of it. Sharing the binary cache in the container registry on the GitLab repo will be very nice, and that way everyone can benefit from the same binary cache. And automatic testing. The big part is by putting it into CI, we now enable multiple people to be able to make modifications. So anyone can branch, and because I have several people come and say, when's that new Intel? I need the new Python. I need a new CMake. I need a new Git. We can have multiple people on the team fork, make the change, submit it, try and get CI, see what is or isn't failing, and then we can start coming together to start working on fixing those issues. But being the focal point of that at the moment is kind of, it's a lot of pressure. Making the binary caches available to our users is something we keep hoping for, but we're not ever quite there yet, because there's always just some small modifications that we're using, or their use case is not quite the same. Trying to reduce the variety of libraries, which Chris has for a long time, might help with that, but we'll just keep on trying. And then providing containerized builds of pre-releases would be nice for the users, so they could test before it becomes the production instance. And we break everything for them, and now we have to roll back and try and figure that out. Knowing that ahead of time would be very nice as well. And if we have CI that's doing this, they can pull the containers, build themselves, run it, test it, and give us the thumbs up or thumbs down. And then, well, user-generated programming environments. Some places have this. I think CSCS kind of has this, where you just mount in your own installation of your own stack, and that's just what it looks like. We can do that with containers or unshare or a number of different ways if our users get to that point, and we would like to help with that because we can make performant things. But yeah, that's another one of the ideals. So that's the state of our environments, how we're dealing with them, issues we've hit. Thank you.
All right, we're really short on time, so I think that Sean should start making his way up here, but we maybe have time for one question if someone has one. Okay. Oh my gosh. You both asked questions. Yeah. Okay. Here you go.
Just a quick comment. I know there is a lot of historical versions that you had to work with. Obviously, some of us are coming into this a little new. I guess maybe in the long term, do you see any kind of best practices coming out of it? I see environments as one. That's one thing I was thinking of.
Yeah, I think having a build cache will be helpful. I've thought about being able to remove some of that old software, but offer a container that still has it for any of those few stragglers that are left. The one thing we've leveraged is being able to take a full environment, have that be a concrete spec, build it, put it in place, and then add on to it in using a spec that is not even the same version as that initial one was. And by just leaving it the same, it's a concrete pile of software that we don't have to worry about trying to reinstall anymore. Yeah, so that's what we've tried on that subject.
All right, thank you so much.